So in this video, we're going to look at the conversion of an acid chloride to an amide. So your acid chlorides are your most reactive carboxylic acid derivatives, so we can easily convert them into our less reactive carboxylic acid derivatives. So here is the general structure of an acid chloride. And if we are converting this acid chloride to an amine, we are going to use two equivalents of the amine. So we will say two equivalents, and I'm just going to draw for our first example of a primary amine, and this would form the amide product. Okay, so we would get, so let's make that R group different, R prime. So this is kind of our overall reaction that we're looking at. So first of all, I want to look at some restrictions that we have on this, and then we'll look at an example and run through the mechanism. So notice that with this primary amine that I use, we start with an NH2 and we have NH in the product. So we need to have, for this to be successful, we need to have a hydrogen on that amine that can be removed. Okay, and we do need to have two equivalents of the amine. And so specifically that amine can be ammonia. So that would be just NH3, or it could be a primary or secondary amine. So it cannot be a tertiary amine, because the tertiary amine would not have a hydrogen that could be removed. So let's take a look at this overall reaction. We'll run through the mechanism and see why it is that we need two equivalents of the amine in order for this reaction to work. So let's look at an example. So let's say that we want to make the following amine, or amide. So let's just draw an amide. Okay, so from this structure, we can break down what portion of it is coming from the acid chloride and what portion is coming from the amine, right? The chlorine is your leaving group, right? And that's going to be replaced by a nucleophile. So if you're looking at your general structure, you could look at this here. And that tells you what the nucleophile needs to be. It tells you what amine you need to start with. Right, because we see that this structure is the amine that you started with one extra hydrogen. Right, so that's where it's coming from. So if we're going to break this down, we're going to say that this is the portion that's coming from the amine. And the portion that contains your carbonyl is clearly what's coming from that acid chloride. Okay, so what we're going to say is that to make this, then we need this 1, 2, 3, 4 carbon atom acid chloride. And then our amine, we see NH, we're going to add one more hydrogen, so it'll be an NH2, and here's a bond to CH3. So we need here two equivalents of methylamine. All right, so let's take a look at the mechanism and see if we can explain, why we need those two equivalents. So this is a neutral nucleophile, and you're only going to see this reaction with a neutral nucleophile because a negatively charged amine is extremely basic. It's a really, really, really strong base. So we're going to use just the neutral amines for these reactions. So I will draw one equivalent of this amine. So here, this is the first equivalent. And this is going to attack the carbonyl carbon, which is electrophilic. And that pushes those electrons up onto the oxygen. And so what that does is it generates a tetrahedral intermediate. So we're going to go this way for the mechanism, just not to confuse it with the overall reaction that we're going to write. So we have here, we have a new bond from the nitrogen to this carbon, and we broke the pi bond, so now we just have a single bond to oxygen. So our oxygen has a negative charge. We still have the chlorine. And then we have the new bond to the nitrogen, and that nitrogen has two hydrogens and a methyl group. So we've got this protonated nitrogen. And so what's going to happen here, this is your tetrahedral intermediate because we went from an sp2 trigonal planar carbon to an sp3 tetrahedral carbon. So this is the tetrahedral intermediate. And so these electrons on the oxygen can come back down and form a pi bond and push off the leaving group. And then you're going to have something that looks a lot like the amide product that we're looking for, but it just still has an extra proton. And so here's where that second equivalent of the amine comes into play. That second equivalent is going to remove one of these acidic hydrogens. So this is your second equivalent of amine. And so what this will do is it will remove one of these protons, giving those electrons to the nitrogen, thereby making it go to a neutral nitrogen, right? Because it's gaining some electrons. So then our overall product here is going to be the amide, right? The one that we were looking for, the CH3. And then we'll look at what the byproducts were. So now we're going to have also this protonated amine, right? So it was NH2, it grabbed another one, so it's NH3 plus. And it's got the chloride would be associated with this. This would be an ammonium salt. Okay, so what we've got here in the center, we went down and did the mechanism, but across here is like that overall reaction scheme. So if you weren't drawing the mechanism and you're just saying, I have this acid chloride and 2 equivalents of the amine, and it's going to form the amide and that ammonium salt. And so the amide, of course, would be your major organic product that you're looking for. And we can go back now and we can complete this top structure to say where that second equivalent of the amine is, because you're also going to make an ammonium salt here as well. All right, so that's the byproduct of the reaction. So this is a byproduct. Ammonium salt. And so that would probably be removed from your major organic product by something like an extraction, right? That might be water soluble and this might be organic soluble. So you should be able to throw them in a separatory funnel and separate them.